Hello everyone, I am Dr. P.S.V.Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the extrinsic semiconductors. Actually, the semiconductors are classified into two categories as intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors are pure form of semiconductors. Okay, whereas extrinsic semiconductors are impure or doped semiconductors. At the end of this lecture, student will able to understand the crystal structure of extrinsic semiconductors, and you can also able to understand the carrier concentration of extrinsic semiconductors. Now coming to the extrinsic semiconductors, actually the intrinsic semiconductors are silicon and germanium. Already we know that. Whereas extrinsic semiconductors are impure semiconductors or doped semiconductors. They are of two types, N-type semiconductor and P-type semiconductor. So when do we get N-type semiconductor? When do we get a P-type semiconductor? That what we are going to see now. And so in this one, coming to the crystal structure of this one, observe actually when the fifth group elements like phosphorus, the fifth group elements like phosphorus, arsenic, etc. are added to the fourth group elements like silicon, germanium crystals, then N-type semiconductor is formed. So these are the impurity atoms in this one are the pentavalent elements like phosphorus and arsenic. So when a phosphorus impurity is added to the silicon crystal, what happens? Actually in the silicon crystal, each silicon atom is containing the valency 4. There are 4 valence electrons. Of course, they are in bonding like with the other electrons, they are forming the covalent bonding. But whereas coming to the fifth group elements, either phosphorus or arsenic is added, it is containing 5 valence electrons. Observe this diagram. This phosphorus impurity is having 5 valence electrons. Out of 5 electrons, 4 electrons are forming 4 covalent bonds with the neighboring silicon electrons. What about the fifth electron? This is not a free electron. This is in the loosely bound state of phosphorus. So, at T is equal to 0 degree Kelvin. This phosphorus is not at all donating the fifth electron, and there are no free electrons in the silicon crystal. That's why this material also behaves like an insulator. At T is equal to 0 degree Kelvin. At T is equal to 0 K, there are no free electrons at all. Okay, now just raising the temperature, what happens? You just give a little bit thermal energy KT, give the temperature. What happens? So, first of all, this phosphorus impurity that donates the fifth electron to the crystal. That's why it is called donor impurity. It is donating an electron. Like that, all the phosphorus impurities will donate the electrons to the crystal. That's why they lie just below the bottom edge of the conduction band. Observe, this is the conduction band as usual, the valence band, and in between these two, there are some extra energy levels called donor levels or donor impurities. All these things are phosphorus impurities. At T is equal to 0 degree Kelvin. These phosphorus atoms are not ionized, electrons are not promoted from the valency band to conduction band. That's why there are no free electrons in the conduction band, no holes in the valency band. If this material is connected to a battery, the external circuit, as there are no carriers, it will not conduct the electricity. That's why this material is also acting like an insulator. Raising the temperature, it is donating the electrons. What happens? One electron goes to the conduction band from the donor levels. Suppose one electron is going to the conduction band. What happens? This becomes P plus ion. Similarly, one more electron goes to conduction band, one more P plus ions. In that way, by raising the temperature, initially electrons will be promoted to the conduction band from the donor levels. As a result, electron density increases, ionized donor level density increases, there are no holes in the valence band. Initially at low temperatures. As the temperature increases rapidly, what happens? After completion of this ionization process, electron will go to the conduction band from the valence band, creating a hole. Again, one more electron goes to conduction band, one more hole is created. Here, electron density is very high and holes density is less. That's why electrons are called majority carriers, holes are called minority carriers. Electrons are negatively charged carriers. Moreover, the most of the current is mainly due to the negative charges. That's why this material is called N-type semiconductor. The negative type of carriers, electrons are responsible for electrical conduction. That's why this kind of extrinsic semiconductor is called N-type semiconductor. So, if you observe this diagram at T greater than 0 degree Kelvin, this is the carrier concentration expression. Nn, electron density in the conduction band Nn is equal to Nd plus Pn. Suffix N is representing N-type semiconductor. As usual, N is representing electron density, P is representing the holes density. What is this Nd plus? Nd plus is called ionized donor level density. So, the number of electrons is equal to number of ionized donor levels plus number of holes. For example, in this one there are 100 electrons. So, only 80 donor levels are ionized. Definitely 20 holes we can find, means 20 electrons have been promoted to the conduction band from the valence band. The number of electrons is equal to number of ionized donor levels plus number of holes. Once you observe this equation, number of negative charges is equal to number of positive charges. Charge is neutralized. That may be N-type semiconductor or P-type semiconductor. It is electrically neutral. We should not take N-type semiconductor means it is negative material. Not like that. It is electrically neutral. Charge neutrality is maintained. So, this is the expression for electrical, electron density or carrier concentration. So, in the N-type semiconductor, simply the fifth group element phosphorus or arsenic is added automatically. So, at T is equal to 0 K, it is acting like an insulator. Other than 0 degree Kelvin, the phosphorus is donating the electrons. That's why we can find some electrons in the conduction band. At high temperatures, electrons are promoted to the conduction band from the valence band, and this is the expression for electron density. And similarly, coming to P-type semiconductor. So, when a P-type semiconductor is formed, as usual, the third group elements like boron and aluminum, not phosphorus. Phosphorus is the fifth group element, we get N-type semiconductor. So, boron and aluminum are added to the fourth group silicon or germanium. So, we get a P-type semiconductor. Suppose, let us take an example, aluminum is added. Aluminum is a trivalent impurity, whereas silicon or germanium is the fourth group element. Of course, to form the 4 covalent bonds, there is a deficiency of electron. So, it is indirectly taken as a whole. So, 4 covalent bonds are formed in this one. 4 covalent bonds are formed with a deficiency of electron, nothing but hole. But one thing, this hole is not a fixed one. Sometimes it may be there here, or this electron comes to this place and here hole is formed, and this electron comes to this place and hole is formed. That's why we can say this hole is in the loosely bound state. At T is equal to 0 degree Kelvin, there are no free electrons, no free holes in the crystal. Again, this material also behaves like an insulator. So, coming to the energy band diagram in this one, as usual there is a conduction band and valence band. These aluminum impurities are third group element, they are called acceptor levels. Why they are called acceptor levels? You just raise a little bit energy, electron will go to the acceptor levels, and this will be formed, means the electron from the adjacent silicon, it comes to this place, this bond will be completed, and whereas in the silicon crystal a free hole is formed. If again temperature is raised from the next aluminum, that also extracts an electron from the adjacent silicon crystal. In that way, all these impurities are boron impurities or aluminum impurities, they are accepting the electrons from the silicon crystal. That's why they are called acceptor impurities. So, for this purpose, they are lying just above the valence band edge, EV. Above the valence band edge, they lie. Observe the energy band diagram in this one. So, this is the conduction band. The lower edge of the conduction band is taken as EC, and this is the valence band. Upper edge of the valence band is taken as EV, and above this one, there are the acceptor energy levels like boron, aluminum. So, initially, there are no free electrons, no free holes, but simply raising the temperature T greater than 0 degree Kelvin, what happens? Electron will go to the aluminum impurities or boron acceptor levels. Suppose it is boron, you will get B minus, aluminum Al minus you will get. So electrons will go to these impurities, all will become ionized. After completion of, actually one electron is going to this one, what happens? Hole is created. So in that one, without creating the electrons in the conduction band, holes are created in the valency band. When this is connected to the external circuit, what happens? All these holes will produce the current or electrical conduction. The electrical conduction is mainly due to holes. Holes are positive charges. That's why this material is called a p-type semiconductor. Okay, again raising the temperature to higher levels, what happens? At high temperatures, electrons will go to the conduction band, just like intrinsic process. So you can find the electrons in the conduction band, holes are created in the valence band. You observe, now the electrons are minority carriers, holes are majority carriers. In case of n-type semiconductor, electrons are the majority carriers, holes are minority carriers in n-type semiconductor. Whereas in p-type semiconductor, holes are the majority carriers, electrons are minorities. One or two minority carriers may be there, but the most of the current is mainly due to the holes positive charges. That's why it is called a p-type semiconductor. Now coming to the holes density in the valence band. How do we write the holes density? That is denoted by Pp is equal to Na minus plus Np. What is this Pp? Suffix P is representing the type of the material, p-type semiconductor. Everywhere for holes density is taken as P, electron density is taken as N. Always holes lie in the valence band. So this Pp is equal to Na minus plus Np. What is this Na minus? Na minus is the acceptor level density, ionized acceptor level density. So the number of holes in this one is equivalent to number of ionized acceptor levels, number of electrons. You observe, as just like the previous one, if 100 holes are there, acceptor levels are ionized, definitely you can find here 20 electrons. 100 is equal to 80 plus 20. Pp is equal to Na minus plus Np. So the holes density is equal to acceptor level density plus electrons density. Number of positive charges is equal to number of negative charges. Again, the charge is neutralized. Charge neutrality principle satisfied here. So this is the expression for the holes density. Coming to the summary of this one, what we have discussed in this one is the structure of the extrinsic semiconductors. First of all, the extrinsic semiconductors are impure semiconductors or doped semiconductors. They are of two types, n-type and p-type. N-type semiconductor is formed when the fifth group elements like phosphorus, arsenic, etc. are added to the fourth group silicon and germanium, and crystal structure we have seen. And later on, the energy band diagrams you have seen, and corresponding the electron density in the n-type semiconductor, holes density in the p-type semiconductor also we have seen. Okay, thank you very much.